One. It's 11:30, time to start the next talk. I'd like to welcome Benjamin Peterson, going to tell us all about garbage collection in Python. Thanks, Benjamin.
Thank you, guys. I'm happy to be here. We're in the big room today. I always try to read something into where the PyCon organizers put me, and I assume that they put me in the big room so they can embarrass me when no one shows up. But you guys are proving them wrong. Thank you. So what am I going to cover in this talk? Well, mainly I'd like to talk about how we actually implement garbage collection in two of the main Python implementations, namely CPython and PyPy. And in particular, in the case of PyPy, I'd like to address the issue of optimizations and what sort of patterns we see in Python which lead to the need for certain optimizations and how PyPy does that. And finally, I'd like to spend a few minutes talking about various issues which in the intersection of language design and garbage collection, where garbage collection actually causes us to have to think about the semantics of Python and how we want that to be. Okay, so we'll start with some implementation basics. And as I said, I'm only going to talk about PyPy and CPython, and that's mostly because those are the only two which I have worked on and have knowledge on. I do not want to say anything bad about the IronPython or Jython GCs, but they inherit them from their language implementations and not written specifically for Python, unlike the CPython and PyPy. So the most basic question we're going to ask is, what do we mean by garbage collection in any language, and more specifically Python? Well, what we usually think is that objects which are no longer reachable by our program will be deallocated and the resources they're using cleaned up so new objects can take their place. A somewhat subtle question is, when are we going to get our objects cleaned up? And the Python language reference, which is sort of the standard, is very cagey about this. It says, objects will eventually be cleaned up or never. So in theory, you can make a Python implementation which just called exit at the end and the kernel cleaned up everything for you. But that probably would not pass muster. And what we'd really like is that objects are cleaned up at some point before we run out of memory. So CPython, venerable old reference implementation. The primary garbage collection is reference counting. The idea is very simple. Basically, the objects which are reachable in your program have a count which says how many people want them to still be alive, as how many people are expecting to be able to use them, other objects that is. And so when you first create an object, there's one piece of code or one other object will be referenced, and so it'll have a reference count of 1. And then that will go up and down as other parts of the program use it. And finally, when the object reaches a ref count of 0, we know it can be safely deallocated. So here's my diagram of how that works. And we're going to imagine that these objects here are pre-existing, and during the course of the program, we'll allocate another object called object C. And since it's a new object, it'll have a ref count of 1. And then say if object B now gets a reference to object C, then the ref count of object C will become 2, because it has 2 links in the graph here. And then if another object is allocated and handed to objects, and object D gets object C gets a reference to the new object D, then once again, object D will have a ref count of 1. Now, what happens when object C is no longer accessible from the live program? Well, the links are broken, and so each time a link is broken, the ref count is decremented by 1. And since there are no longer any links here, the ref count will be 0, and we'll realize that the object can be cleaned up. And in the process of its cleanup, it will remove all the references it has to object D, and so object D will also become a dead object, and they can be reclaimed. So if you ever looked at the CPython source, it's littered with these macros, pyincref and pydecref. So here's an example, and these are the operations which actually do reference counting in CPython. I put in a simplified example of how this works So this is the code which sets items in a list, just a normal Python list. So this is the list which you're setting in. This is the index which of the item you're setting, and this is what you're actually will be setting. And so you see the list takes a reference to the v, which is the object you're putting into the list, because the list is now going to own it. This is the code which actually puts the item at the index you expect. And then finally, it decrements the old value which it was holding in that index in the list. So it can be cleaned up because the list is no longer referencing it. One subtlety in this piece of code you may notice is that we very carefully put the new item in the list before we deallocate or decrement the ref count of the old value. And that's because if you decremented the ref count of the old value before you had put the new item in the list, it's possible that some Python code could run which would touch the list and would see an uninitialized value at that place index in the list. Okay, so reference counting is an old idea, and it works pretty well as the main garbage collection in CPython, but it has a major flaw, which is that if you have references which are in cycles, they will stay alive forever with pure reference counting. And so what happens if, going back to our example, is that if you have an object here, C, and an object here, D, and they both reference each other, well, the number of links going into object C are 2, and because there's one coming from D and one coming from the older objects, and object D has a ref count of 1, and even now if we drop the link from the pre-existing objects, so it's no longer referenced in our program, then both of these objects will still have a positive ref count because they still reference each other even if they're not accessible from the program. So CPython has a separate garbage collector called the cyclic GC, which detects reference cycles and removes them. And so unlike reference counting, where you immediately know once an object is unreachable that you can deallocate it, the cyclic GC runs every once in a while to detect and deallocate cycles. And this is what you're actually invoking when you run GC collect on CPython. And the operation of the cyclic GC is very simple. Basically, it looks for all cycles in the program, and then it decrements the internal references of the cycles. So that's what's happened here. If it's during the cyclic garbage collection, the internal references in cycles are decremented, and then if the objects in the cycles reach 0, then you know that it's a cycle which is not reachable because the references were only due to internal cyclic ones. So we're able to deallocate it. Okay, now I'm going to switch to what I consider the more interesting part of the talk, which is PyPy. So let me briefly review the basics of PyPy. So PyPy is written in a restricted subset of Python called rPython. And the rPython can be translated to a lower-level language. Right now, that's primarily C. And since the interpreter is written in Python, it's actually has garbage collection. rPython is a garbage collected language. So as the rPython is being lowered to C, garbage collection has to be added. And so what that means is that the interpreter is actually abstracted away from the garbage collection implementation, unlike CPython, which is littered with artifacts of ref counting. So that means you can change the garbage collection implementation at translation time, which is the lowering of rPython to C. So as I said, the PyPy GC is just another low-level transformation of the rPython object graph. And the garbage collection implementation is actually written in rPython itself. So you can go look at the source code. It's very strange to see this rPython code, which is actually working with raw memory once it's translated to C. And it also means it can be tested in Python. You can run it on the Python interpreter, and you'll get normal exceptions when it's not translated to C. And so there have been quite a lot of PyPy garbage collection implementations over the years. The current one is called Minimark, and it's what I'll be discussing the basics of. So PyPy does not use reference counting by default, and so it uses a more traditional garbage collection scheme, I guess you could say, called mark and sweep. But the idea is also very simple. Basically, you start with objects which you know are alive in the garbage collection phase, and then you walk their references all the way out, and then while you're doing that, you carefully mark them to say, oh, I know this object is alive. And then after doing that, you move to something called the sweep phase, where you walk all the objects which you know about in the program, and if they're not marked, you know they can be deallocated. And so this has no problem with reference cycles because there's no reference counting, and you will just see the cycle as not reachable. So here's the visualization of this. So again, we have our newly allocated objects here, and now we're in the marking phase. So we're assuming that we know these objects are alive, object A and B, and the garbage collector will traverse these links. It'll see object C. It will mark object C, it knows it's alive. And then in the next phase of garbage collection, sweeping, it will walk all these objects. We'll see object A, B, and C are marked, so they are alive. But object D is not marked, so we know it can be deallocated. So what's really interesting is how we can use parts of observations of the Python language usage patterns to optimize garbage collector implementation. So one of the primary observations of Python, and indeed most dynamic languages, is that you are often allocating lots of objects which are soon thrown away. So I've put a few examples up here. So traditionally, you'll be allocating lots of intermediate float objects in this simple average, which will be thrown away before they're stored in a variable. And for example, if you have every time you iterate over something in Python, you iterate an iterator object. It's very transparent, but you do actually have to allocate it internally. And anytime you call an object on a method, you have to allocate a bound method, which actually binds the self object to the method, so you don't have to pass self. And then another common pattern in Python is long strings of replacements. So like this is some code which I found in Jinja to do HTML escaping. And so each one of these things creates an intermediate string object, which is then immediately not used after you move to the next replace call. And so in the GC garbage collection community, this goes by the rather macabre title, High Infant Mortality. Basically expressing the idea that you have many young objects which do not live very long. Continuing the dark metaphor, the optimization we use to help with this is called the nursery. And so the idea in the nursery is that whenever you allocate a new object, you put in this small little buffer, and then you just garbage collect the nursery very often, much more than you collect the entire object graph. And so if an object survives a nursery collection, then you move it into an older generation, which is not garbage collected so much, under the assumption that it will live longer than the things which were garbage collected in the nursery. And so this seems pretty simple, but there's one subtle point, that is you actually have to be moving objects around in memory to implement this. And so what that means is that PyPy GC has the ability to move objects, that is, copy them to different parts of the RAM, while also updating the internal pointers to which other objects might have to that new object. And so that's very much showcases the flexibility of the PyPy model, because when we have the entire interpreter being translated to C, we can see which objects will have internal references to other objects, so the garbage collector can perfectly update internal references. Another thing which PyPy tries to address is GC pauses. So basically, in a traditional garbage collector and CPython cyclic garbage collector, when the garbage collector is running, your program is not running. It just stops the program so it can safely walk the object graph. And so sometimes people will have massive servers with a lot of objects allocated, and the GC will stop their program for like half a second, which is bad. But this becomes especially prevalent if you're trying to do real-time things like video processing. Of course, no one tried to do video processing with Python before PyPy came along and made it actually reasonable to do that sort of computational stuff with its just-in-time compiler. But now it's actually become a possibility, and so GC posits have become more of a problem. So PyPy has something called an incremental garbage collector. And what that means is that instead of doing the whole mark sweep process in one go, stopping the program completely, it can do a small part of the marking process and then let the program run some more and then doing the next part of the marking process. And as you can imagine, that's not terribly simple to do because it's easier when you assume that the program is being stopped and you won't be mutating other objects. But according to the PyPy blog post where Armin and Magic implemented this, it was actually relatively painless to do. So go PyPy. And so this means that you can break down the garbage collection time into just a few milliseconds, which shouldn't be noticeable in real-time processing kind of applications. So in summary, the attributes, if someone asks you, what is great about the PyPy GC, you should tell them, well, you can choose what kind of garbage collector you want. And it also has a nursery. So a generational garbage collector is one which has the objects in different categories based on how long they've been alive. You can say it's incremental, and it's also integrated with the just-in-time compiler. So the last few minutes I'd like to spend talking about some subtleties of garbage collection semantics. Specifically, I'd like to talk about del, which I think anybody who's been in Python for a little while will have bad experiences with del. And so the main problem with del is that when objects are deallocated, it can be a fairly arbitrary point in the program. And so if you start running arbitrary Python code at an arbitrary point in your program, stuff might not be initialized, or you might be in some weird part and shut down. So that's one part of the unsafeness. The other part is that if you have finalizers which are in a cycle, then it's hard to know which one to deallocate first. Because so in this example, the finalizer in object C the object C has a reference to object D, so it could try to fetch attributes of object D or call a method on it. And the same thing is true of object D. And so you don't know which one is safe to call first because they might be trying to use the attributes of each other, so it's a tangled web. And so the solution to this in CPython for a long time has been to just not run finalizers, which are in cycles. And what that actually means is that cycles which contain finalizers would get moved to this list in the garbage collection module called gc.garbage. And so it would essentially leak them. And in theory, you could sift through this list and deallocate them safely. But a lot of people didn't know about this, so if they suddenly had finalizers and cycles, then they would essentially be lost. But this problem has been addressed in CPython 3.4 with something called PEP 442. I'll talk about that in a second. And PyPy has always tried to run the finalizers in a reasonable order. And reasonable in this case means you roughly do a topological sort of the object graph. And so you try to run the ones which have the least dependencies first. But at the end, you pretty much just have to pick an arbitrary finalizer to run it because the garbage collector does not know which one is safe to run. So specifically in, specifically in PEP 442 in CPython, this is the work of a CPython developer named Antoine Petrot. It proposed slightly modifying the cyclic garbage collector in CPython. And the way it works now is that you detect all the cycles in the program, and then you you run finalizers on them, and then you see if the finalizers resurrect the objects, because that's also something you can do in a finalizer. And then if the objects continue to be dead and do not add themselves to the alive part of the program, then you can safely clear them. So this allows cycles with finalizers to finally be allocated and removed an annoying source of quasi-leaks in CPython programs. Okay, so coming to the end of my talk, let me remind you of what something which I'd like to get across, which is that garbage collection can be a very subtle and difficult topic, but also garbage collectors are awesome, and especially PyPys. So you should use PyPy. And with that, I will conclude my talk. And if anyone would like to line up for questions, let me point you to some other sources of information. This is a big topic, and I have not covered all the many things which are interesting to talk about. For example, I did not talk about weak references at all. And you can always look at the Wikipedia article, or the source is always the authoritative source of truth. All right.
Okay, so you've got your nursery, and your nursery has all the fresh objects that you're making, and you're keeping track of all the pointers you're making into that nursery. Is there an explicit way to say, make a new nursery, and if you're halfway through, then go, actually, you know what, discard this nursery, i.e. software transactional memory? Has anyone been looking into that?
So there's not a way to control this with a Python program. I'm not quite sure with how garbage collection works in the software transactional memory. I've not been working on that, so you'd have to ask Armin, who's been working on that. But I do know that the garbage collector has very deep integration with the software transactional memory implementation in PyPy.
Okay, thanks for the talk. One of the things that I've noticed is most of the more recent developments in garbage collection all assume that the garbage collection process is asynchronous. So it happens at some arbitrary point in time after the object becomes collectible. Is there any, in the pluggable part of PyPy, is there any way to implement a garbage collector that would have a more synchronous behavior that's closer to the reference counts has reached 0, clean it up now? Yeah, so PyPy has actually had a reference counting garbage collection implementation just to show that you could do it. It was pretty inefficient. So it's certainly possible to do, but I think the common feeling among most garbage collection researchers is that asynchronous garbage collectors allow for a lot more power and flexibility in optimizing them. So it's certainly possible in PyPy's model, but it's probably not something you would actually want to use.
Hi, thanks for the talk. I was just wondering, the PyPy nursery sounds like the exact same thing as the Java Eden space. Is there some notable difference that I'm missing?
No, I think they're very similar. I mean, they differ in small details, but a lot of this stuff was, a lot of everything which we've been implementing in dynamic languages now was in scheme interpreters in the 80s, so okay. We're just deploying. And this also shares a lot of stuff with modern JavaScript garbage collectors like V8 and SpiderMonkey also do this kind of thing. So it's a very, as I was saying, it's a very common idea in the implementation of dynamic languages.
Okay, and then also I was taking some notes, so I might have missed this. Is there 2 survival spaces, like what the Java garbage collector has, for young generation stuff, or does PyPy do something else?
So in the current implementation, there's sort of 2. There's the nursery, and then there's the tenure generation. But there's in one of the other garbage collectors, you can have more generations. In fact, in the CPython cyclic garbage collector has 3 generations, I think now.
Okay, thanks.
Hey, so Building on the previous question, there are a lot of languages in the bigger family tree that Python belongs to, all the way from Smalltalk's various incarnations through Self and E, as well as JavaScript. And I was wondering if there are, amongst the many different the many different GCs that PyPy has, if there are any new research directions for object-based languages that you have been exploring that nobody else has hit upon yet.
Let's see. I have to admit something, which is it's been a while since I've worked intensively on the PyPy garbage collector. So you might have to ask Armin, or there's another guy named Carl Friedrich Bowles about that. I can't think of anything off the top of my head. Sorry.
No worries. Thank you very much.
Hi. For both CPython and PyPy, how do the garbage collectors deal with fragmentation?
Yeah, so CPython, once you allocate an object, it's there forever. So it's pretty much a function of how good your heap allocator is, your underlying memory allocator. Well, it kind of actually depends on the platform. So CPython has its own memory allocation sort of thing called obmalloc, which in theory should reduce the fragmentation and be faster for Python programs, but you're kind of stuck where you put the object, and you can write programs which cause a lot of fragmentation. In PyPy, since you can move the objects around, one of the things you can do is kind of compact all the objects into one part of the memory in order to reduce fragmentation. So PyPy can certainly address that.
Cool, thanks.
Thank you for coming.
Looks like that's it for questions. Thanks, everyone. Thanks, Benjamin.